Started with this concept. The first problem was the marbles were jamming in the distributor. Second, and this is the bigger problem, is the marbles often end up like this, so they don't even make it into the distributor. I thought that maybe adding an agitator right here would help, but then I had the idea to combine both things into one single
So
thing
welcome
using an
everyone.
Archimedes screw. But I couldn't really figure out
Good
exactly.
evening to all. So today we are starting with our Astro Talk number 33 with respect to Amateur Astronomers Association. And today we have the topic exploring the universe with the radio astronomy, or I would more uh, explain ways amateur astronomy with the GMRT through RAD at home citizen science research. So when we talk about radio astronomy, it basically unveils the cosmic mysteries by detecting radio waves from celestial objects like galaxies, pulsars, and black holes, or even supermassive black holes. However, unlikely like optical telescope, radio telescopes can operate independently, unveiling the hidden cosmic phenomena. Amateur astronomers can engage in a real discoveries through these initiatives, like RAD at home, using GMRT, the world's largest radio telescope. So I welcome everyone for this science program to analyze the real data and contribute to the groundbreaking astronomy research. So today's our speaker is Anand Hota, Dr. Anand Hota. Okay, he is currently serving as an university grant commissioner at UM-DAE Center for Excellence in Basic Science from University of Mumbai. He is actually the founder, director, and principal investigator of RAD at Home, pronounced as RAD at Home, Astronomic Collaborative at a UCC Startup for Citizen Science Research in India, launched on 15 April 2013. It is the first Indian citizen science research platform in astronomy. Recently, Anandji has obtained his PhD in astronomy and astrophysics jointly from NCRS and TFR in Pune and Indian Institute of Science in Bangalore in year 2007. He has worked in multiple institutions like GMRT Observatory, then Ayuka Pune. Then he has returned to India in year 2012 to launch the first Indian citizen science research platform in astronomy, currently as known as RAD at Home. He is a member of International Astronomical Union, Astronomical Society of India, and Square Kilometer Area India Consortium. For his international news-making astronomical discoveries and founding RAD at Home Citizen Science Research in Indian Astronomy, he has been awarded as Samanta Chandrasekhar Jyotirbian Samman, facilitated by Honorable Chief Minister of India and Director of ISAR Kolkata and ISAR Bareilly. His astronomical discoveries has made international news four times. First in 2011, and then 2012, 2013, and recently in 2022 also. This discovery has been press released by NASA, JPL, Caltech in USA, and Royal Astronomical Society in UK, National Astronomical Society in Japan. This has created a lot of Google hits, social media views, bringing pride to the dunia. His main field of research is multi-wavelength observation of black hole galaxies. His citizen science research initiative, RAD at Home, involves people in making discoveries using GMRT radio telescope, the largest such in the world and the pride for India. RAD at Home has been appreciated and supported by Nature Index, IUU, SKA, like international organizations, as well as 2 dozen of research institutes all over the India. It has trained thousands of citizens and university students involved into astronomy. He explains to the audience in a such simple words what he has discovered the exotic stars, galaxies, and supergiant black holes. He encourages university level science educated public to join his citizen science research via Red at Home e-classes every Saturday at 9:05. So today with this, I welcome Dr. Anand Hota to our Astro Talk 33 for exploring the universe with the radio astronomy. Welcome Anandji. Over to you.
Thank you, Mangesh ji. Thank you very much for that kind introduction. Uh, I was looking at the people's videos, and there are many young students,
Correct.
school level students.
Yes.
So I assume one third of them are school students, and rest are high school or university level people,
Correct.
or higher than that. So um, Before I begin my slide presentation, let me start this simple way that typically amateur astronomy people think that we will go to a star party through the telescope, we will watch the stars, we will gain some knowledge, and if our career permits, we will become a science student or something else. If I am a science student and I still am a amateur astronomer, what should I do? I will go to bigger star party, understand little more because I have learned little more physics and chemistry and mathematics, how planets move, how galaxy black hole attracts, how Big Bang started, many concepts of astronomy. You will start learning because you are in the college level. And in the modern day, college education, BSc, MSc, it requires a project component. And now everybody knows that unless we do a project, probably our education is not complete or we are not a good in education. What will you do after MSc, BSc? Suppose you are still interested in astronomy and want to have a career in science, then you want to apply for a MS or PhD, trying to do PhD in future. And suppose you continue to do your amateur astronomy. Why not do that amateur astronomy? Continue to make that amateur astronomy hobby of yours to do a project in astronomy. That is how lot of students are interested in their BSc, MSc level to do a project in astronomy. But they struggle to find who will be the guide to the astronomy project that they want to do. Their colleges may not be having a PhD degree holding astronomer as their teacher so that they can do a project in their college. So they look for a project guide somewhere else. If they write to big research institutes, then they will say that you come through our astronomy summer training or winter school. You do a internship. So they have to apply for an internship. If they get selected, then they can do a project in astronomy research institutes. As you all know, that research in India are in the field of astronomy mostly confined in research institutes in astronomy. For example, TIFR, NCRA, IUCA, IIA, PRL, IIST. There are many astronomy research institutes where astronomers are there. They have big telescope, they have big facility, they have international class research, they publish international quality research paper. Now, where will the student go to do a research? To these institutes. Now, India has a lot more students than the research institutes can handle. For example, ICERs. I'm in a similar system to ICER, like NICER and CBS, Center for Excellence in Basic Science, Mumbai. There are many students who want to do project. New education policy is requiring many more people to do projects. That is what is the real research-like experience, real field experience. So I develop a feeling that the time has come that we should not simply appreciate the beautiful pictures of our astronomy coming from many sources. We will start measuring the images and getting quantitative data out of those things. Then automatically at school level, at high school level, at university level, everywhere, wherever you are getting an astronomy picture of the day, we can start doing some numbers, calculation, some number from those images. So amateur astronomers, astrophotographers, any any engineer in their profession associated with any reasonable size telescope can contribute to an astronomy project for any level of student. They may directly or indirectly can collaborate with real astronomers who have PhD in astronomy. So there should be a college guide, college lecturer, or school teacher, a engineer, amateur astrophotographer, any kind of engineer is good enough, and the astronomer in some research institute. So there should be this kind of a combined way of approaching, that we all should be giving a new name to amateur astronomy in India to handle the education system that requires a lot of astronomers to be there. But astronomers are not mostly confined to institutes, not available in universities that many. Okay, so with this forward, I believe that all amateur astronomy clubs should have their PowerPoint presentations about various celestial phenomena, and at the same time spend 15 minutes or half an hour after the talks to how to get numerical data, number data, some kind of quantitative calculation of any topic they teach. I will give certain simple examples. For example, this is what I call measuring the moon with a mobile phone. You don't require a telescope. You have a mobile phone. What do? You take photograph of a 15 centimeter scale, small scale, keep it at a wall, standing, and from 1 meter distance or 2 meter distance, whatever, have your mobile phone ready with a maximum zoom and take a photograph. So what is the angle? 15 centimeter, Y, and here X is your 1 meter. What is the angle? Any trigonometry students can find out. Now, that is the angle in your picture that you take out of the mobile phone, take it to computer. There are open source like DS9 where you can open that image. With Google, you convert that JPEG file or PNG file of your mobile phone to a FITS file, FITS, and that FITS file can be opened in a DS9 image viewer. So in DS9, I will teach you later at the end of the talk, measure the size from left end of the mug to the right end of the mug, or the top or bottom of the size of the 15 centimeter scale or cup, anything you can put in. So 15 centimeter in the image is the angle. How many pixel? Say 150 pixel. 150 pixel becomes that much angle. So you have now calibrated your mobile phone. How many pixel is how much angle. Now with the same zoom, at the night, take a photograph of moon. You will see that now moon is a different number of pixels. And what is the angle of the moon? This is how you all know from the Google or from your knowledge by now that moon is roughly half a degree size. 1 degree is 60 arc minute. 1 arc minute is 60 arc second. So moon is half a degree, like roughly like 30 arc minute. You can measure less than a degree or 30 arc minute, few arc second, tens of arc second, very small angle. Next, you take any constellation. Amateur astronomers can teach you any constellation. Can you calculate the angle between first star of the Saptarshi Mandal or Bursa major and the second star? There are 1, 2, 3, 4, 5, 6, 7 stars. Can you measure the angle? Can you measure the angle from here to here? If somebody can tell you what is the distance to the first star of the Saptarshi Mandal, you can now think what is the angle if the second star is also at the same distance. Actually they are not, but the second distance, what is the distance between them in kilometers or in parsec unit? So the time has come that the images of the internet should not only be appreciated for its color and structure, we should also start measure them. How bright is the star? What is the distance between the star? What is the redshift of the galaxy that you see in the picture? What is the temperature of the color that you are appreciating in the stars? Those kind of things will change the whole amateur astronomy community to a knowledge creation system, real involvement in the astronomy, data-driven astronomy-based knowledge. Time has come that we should do this. Now, because it is an online talk, I will rely uh, on a PowerPoint presentation, and from there I will be describing. Okay. Somebody confirm after I share my screen that everything is visible. Can you see my screen?
Yes, we can see the screen. You can just
Okay.
click on that height. Yeah, yeah. Thank you.
Yes, done. So, uh, you all, as you have heard, we will mostly focus on what our giant meteorwave radio telescope can see in the sky. Mostly, a lot of amateur astronomers are aware of the constellation, planets, Milky Way galaxy, supernova in some nebulae, that kind of concepts. But we will focus on what radio telescope can see. So to understand that, it is basically starting of the multi-wavelength astronomy. That we have a telescope, but hardly any people know what kind of things a radio telescope see, and what is the meaning of what seeing means through a radio telescope. Does it actually form an image? Similarly, a ultraviolet image of the sky taken by a space telescope. It is a space telescope, it is an ultraviolet image, so actually our human eye cannot see that picture. So how does it see? Does it see the same thing? X-ray image of the sky. Does it see the same thing? Stars. It certainly does not see the same thing. Okay. For example, if you take an X-ray picture of your body, you will see the shadow of the bone. You do not see the skin. If you take an optical picture, you will see the skin. If you take a infrared picture and take two infrared picture difference, you will see the blood veins taking your blood because there is warmer. If you take ultrasound, you will see the mechanical sound coming from different parts of your body, blood flowing into the heart, blood coming out of your heart. So different tools, different electromagnetic spectrum, imaging in different wavelengths, spectroscopy in different wavelengths, traces different component and different physical processes in the sky. So that is why we will certainly see many different things that optical astronomy cannot see. Radio astronomers see some things that optical astronomy cannot see. Rather, the other way around. We want to have a complete picture. Anything that is there in the sky, how it looks in optical, how it looks in radio, how it looks in X-ray. We want to have an all-round view of that object to completely understand what is happening. A layman example I can give you. Suppose there is swelling in your leg. Optical picture will show you the swelling. If I take an infrared picture, that part will be very hot because there is a lot of blood flow happening in that swelling, inflammation has happened. If I take an X-ray picture, that part may be having a crack in your bone. That is why all these things happen. So unless you have a X-ray, infrared, ultrasound, and optical picture together, you cannot have a proper or holistic or complete understanding of the physical process or whatever happening in that object, in that person's leg, or in that galaxy, or in that star. So that is why a all-round observation. Today these things are called not only multi-wavelength, they are called multi-messenger astronomy. Sometimes neutrinos are also coming from there. Sometimes gravitational wave coming from there. Gamma ray to radio, whatever electromagnetic wavelength spectrum is coming, we will use them all because there are different processes they peak at different wavelengths. Different processes they show themselves up at different wavelengths. We will see that kind of thing slowly. Okay, so this was usually my cover page of my talks. That my name, I was introduced. I am a UGC faculty at UM-DAE Center for Excellence in Basic Science. which is Mumbai University, inside the Mumbai University campus. I lead the Red Home Astronomy Collaboratory. It is not a brick wall institution, it's a virtual institution like thing. Some iconic images of what I do, what discoveries I do, the Red Home that was being described, how GMRT, a large human resource network, and GMRT make discoveries together. One of their discoveries is shown here. And I'm a UGC member, so the logo of my institution basically. Okay, typical. A famous picture from a famous astrophotographer Ajay Talwar. What I am showing here is first half is the beauty. Second meaning is the number. Okay, I will take you to the number from here soon. For example, all the stars that you see are of different brightness and different color. Because it is exposed to several hours or so, so each star is taking a track whenever the exposure finished. They are of different brightness, different color. So simple question, why stars in the sky are of different brightness? Why stars in the sky are of different color? So first thing, suppose we assume that all the stars have equal brightness, then different distance to those stars will lead to different brightness that we see. Actually, that is not so. Different stars are of different brightness. Fine. There is a mix because of different brightness of stars. Intrinsically, they are different wattage. For example, 10-watt bulb, 100-watt bulb, 1000-watt bulb. They are different brightness stars. And they are also different distances. So it makes life much more complicated. There are all kind of brightness in the sky. If you take a telescope, you can see more stars. If you have a naked eye, just look at the sky from city, you can see only few stars. These are the brightest ones, who are nearest ones. Now the next question, can we measure how bright they are? Are they 100-watt? Are they 200-watt bulbs? Similar to that? We should be able to measure it with an instrument, not with the eye. So that if I measure 100-watt, next scientist should come and measure also 100-watt. If he measures something else, it may be within the error. If it is 200, then there is something wrong. Star is not changing every day. So the instrument has to be calibrated, instrument has to be proper, so that my 5 kg is equal to your 5 kg in your balance also. The standardized measurement system is necessary. So calibrated telescopes are necessary. Next question, why they are different color? I am coming to a slide. See, for example, this is picture of a red hot iron. Some part is looking yellowish, some part is looking red, some part is not visible at all in the emitted light, but in the reflected light. You all know that this part is also hot. If we touch, we can find out. If you take our hand close to that, we can also feel the heat. Immediately from here to here, there is no 0 degree temperature, right? So this is hotter, this is hot, and this is relatively cooler. So as you can see in the chart here, the things which are looking this yellow is actually 1200 degree hot. Things which are looking this red, 900 degree. Things which are looking this red, 500 degree. Because it is a thermally heated system, the temperature determines at what wavelength maximum light that object will be radiating. That is what is called a black body. But this is very similar to stars. A star which is looking blue, it's hot, very hot, 10,000, 20,000 degree. A star which is looking like yellow, like our sun, it is 5,000, 6,000 degree. It's just like this. A star which is looking red, it's 5,000 degree. A star which is looking much smaller temperature, or much redder, longer than the red visible light, then it is visible in the infrared. Our Earth will be visible in the infrared. It emits maximum around infrared only, 200 degree, 200 micron, or 150 micron, or say 20 micron, or say 10 micron. that kind of wavelength. If it is a 22 micron, 10 micron kind of level, the temperature at which the planet or the comet will be around 200 degree Kelvin. So that is sub-zero. Okay, that kind of concept will come. So if anybody is interested, you can take a screenshot of this picture. There is no problem. It is a website. Website address can be seen here. You play with this. It is simply the Wien's displacement law. You put the temperature, you will get the peak in the nanometer or micron or meter wavelength. You change the wavelength, you get the temperature. You can play with this. Lambda max T equal to constant. So what I am saying is this picture. We need to understand the color of the sources. The candle flame, blue regions are hotter, yellow regions are less hot. The red looking region is cooler. If I take a 3-filter picture, gelatin paper put in front of your eye, everything looks red because the red filter it absorbs green and blue. That is why only red passes through. Similarly, there are green filter and blue filter can be displayed. So if you have a 3 filter images, you can figure out which region is bright in which wavelength. As we all know from the color picture, blue is bright here on the base, the red is bright in the middle. So this kind of RGB, red, green, blue color combinations can also be done for other wavelength, not just visible wavelength. That is where the multi-wavelength astronomy is starting. Okay. As I was describing, a O and B type star, which is 10,000, 20,000 degree surface temperature, will be looking blue. Blue is white. A sun-like star will be looking yellowish, which is around 7,000, 6,000 degree hot. And much smaller than that, 5,000 degree, a very red looking star. For example, Ardra, our Betelgeuse, there is a red giant. The surface temperature is cooler compared to Swati, the blue star. So this is what is the measurement. Color is now converted to measuring the color, brightness. Anything which is looking blue means it is giving more light in the blue. Here, sorry. Any blue star giving more light in blue band compared to its red band. We should be able to measure how bright it is in blue filter image, how bright it is in the green filter image, how bright this is in red filter image. As you can see, the curve should be like this. So blue filter image brightness will be high, green will be in between, red will be the least brightness. So in Red at Home, we take students beyond the optical picture. Every person who joins Red at Home, thousands have joined, many of them learning and going. This is come and go like every educational system. It's an online Facebook group. Coming to the physics of that any galaxy you want to understand, we will have a combined picture. What we call infrared, optical, UV, combined image. Infrared, optical, UV. Infrared will be in red filter, optical will be in green filter picture, and UV will be in the blue channel. So a RGB picture of IOU type, infrared, optical, UV type, will have 3 telescope data combined. Infrared from the WISE telescope, space telescope of infrared, optical from DSS survey, and ultraviolet from the galaxy survey. So when you combine 3 pictures, infrared, optical, and UV, different part like the candle flame, different part will be bright in different wavelength. Wait a minute. I've got a call, I don't know from where. So this is going fine, I guess. You all can hear me, right? Mangeshji?
Yes, yes. We are.
Okay. Not a call from you, so that's fine. Everybody else can wait. The other combination we do is our focus is radio astronomy. So we will have another radio optical radio combined image. Radio from our own GMRT. It is 150 megahertz image, the huge dish antenna from here to here, 45-meter diameter, 30 of them spread over 25 kilometers. You can see a Tata Sumo vehicle here. You can imagine now how big the antenna is. From one electric pole to another electric pole in your road is 50 meter. It is roughly like 50-meter giant dish antennas. From our own GMRT dish antenna, we will put the images invisible, so we'll put in the red channel. And from American VLA, very large array radio telescope, at a different wavelength, different frequency, 20 centimeter wavelength or 1400 megahertz wavelength, that image we will put in the blue channel. And same optical will be in green for a comparison. This was also optical in the green. This is also optical in the green. So what are we getting? We are getting a image combination tool called RGB Maker, radar from RGB Maker, where we are combining infrared, optical, UV, and radio in GMRT, 2-meter wavelength, optical the same, and radio 20 centimeter wavelength. We are combining this 1, 2, 3, 4, 5 wavelength from 5 different telescope data of the same galaxy in a RGB format. So that which part is hot, which part is warm and cold, which part is more bright, which part is less bright, that kind of structure and color combination will be able to interpret what is the physical meaning, what is the meaning that is saying. For example, the flame, as I said, it is looking blue, means it is hotter. It is looking red, means it is cooler. It is mixed with carbon. That kind of interpretation we are making. Similarly, we'll be having different meaning based on the structure and color or the brightness distribution. Our GMRT is 3 times bigger than the VLA, the American telescope. So we have a very powerful telescope. We should know what it is doing. Okay, so the RGB Maker is extremely simple. You just put your name, you just put the galaxy name. It has taken a standard image size. The standard default image size is 0.12 or 1/8 of the size of moon, that kind of small part of the sky, which will image for you. If you wish, I can show you quickly those things. Here's the tool. Okay, my name is say Ananda. Say for example NGC 3801. The galaxy name M31, M32, anything you can put. I just put a query, submit my query request. It is going to make a infrared optical UV, a radio optical radio, RGB images, 4 images it will create in infrared. If it takes a little longer, then we'll go back to the slide. Otherwise, I will show you here. It is extremely easy. Our purpose is to understand what does that colorful picture mean. Next step is going to measure this picture. What is the brightness? Where is the position? What is the size? How bright it is? How the temperature it is, etc. The image has come. Oh, there are 2 galaxies. Optical picture, infrared UV optical combined picture. For example, you can see now, this galaxy is looking red, bright in infrared. This is also looking bright in infrared, but this is not so bright in infrared. Maybe because the 22 micron emission that is coming from these 2 galaxies, because of star formation process, new stars are forming there, that is not happening in this galaxy. For some reason, this galaxy is not forming that amount of star, although they are roughly at the same distance. So something is happening in that galaxy. Why it is not forming new star? It is like an elliptical galaxy, not like a spiral galaxy. You can see here it's looking bluish. It's looking bluish. Okay, let's go back to the slides. So with this kind of tool, we will quickly see many examples of galactic object as well as extragalactic object. But the radio component will be there. We'll go to that little later. But this is a supernova remnant. Okay, Crab Nebula, M1, optical picture. What will you get in radio picture? Is a fuzzy emission that can be seen. The red is the fuzzy emission. For example, this is the plates or Kritika. You can see the bright stars with the naked eye. The dusty cloud, 200-degree frozen cloud, emitting primarily in the infrared. But stars, the radio telescopes data is also put in. If I put radio telescopes data, red and blue, both are from GMRT and VLA telescope, they do not see the stars. That is why this optical picture is showing the green. Radio picture is seen in pink, both red and blue. So what does it mean? It means that the stars are not radiating significantly. Even the largest radio telescopes cannot see the radio emission from these stars. Instead, what it sees the background galaxies, far, far away galaxies, which are actively accreting matter and creating plasma jets. Although they are black holes, them are active. I'll show you an example. What kind of systems are they? Say, for example, this is a star, A O and B type star. You can see a shell, bow shock like structure, but only in the infrared. The dust, whatever solar wind this star is creating, that is creating a kind of a halo around it, a bubble like thing around it, and that is pushing all the interstellar matter, which are not heat, not hot, but they are very cold. But despite being cold, they are still a black body, emitting around 22 micron. That is why the infrared picture is showing that cell. Optical picture cannot show because there is not 6000-degree hot. There is not ionized. This is the best example. Comet. A comet, 65p gun. It's a wise picture.
Hello.
Yeah, but sir, Anand has got disconnected. So
Yeah, disconnected. Yeah.
Uh-huh.
So as I describe in any RGB image, here the different component of different star and the comet, cold and the hot, are seen distinctly because of their different color, their different wavelength of emission. Here again, a supernova remnant. What I have done, our radio image TGSS from GMRT is in red, infrared image, cold frozen dust, etc. from OIs in green, and hot X-ray, million degree hot X-ray gas in blue. So the supernova cell after the explosion is expanding. When you release the gas from your cycle valve, suddenly the air expands outward, outside of the valve, and that cools down because adiabatic cooling. That kind of cooling has also happened during the supernova explosion. Because of the kind of extreme cooling, the space is very cold, few degree Kelvin or few hundred degree Kelvin to tens of Kelvin. Everything has been cooled down by the expansion process. So you can see the frozen dust and pH component in green. As the supernova cell expands in 10,000, 2,000, 1,000 km per second speed, it is also shock. What is the shock? When the ejecta or the cell expands faster than the speed of sound in the medium, in the space, then it is shock. The shock is also shock heating, HEATING heating. The temperature of that object becomes million degree, and that is giving in X-ray. And when there is a shock also, energy from shock is being transferred to the particles there, free particles there, by a process called Fermi first order and second order acceleration. From the shock, this particle gain energy and gain energy in such a way that the velocity of this proton, neutron, electrons there can be relativistic, close to the speed of light. And at that stage, they emit radio synchrotron radiation. So that is how supernova remnants can be seen in radio as well. Okay, so the radio emission from relativistic particles, charged electrons, protons, infrared emission from frozen cold dust and pH, polycyclic aromatic hydrocarbons, and X-ray emission from the million degree hot thermal plasma. So different component of a supernova explosion can be seen in different wavelengths. How beautiful that is. Similarly, this is another supernova remnant. Instead of putting other thing, I have put radio, infrared. Instead of X-ray, I have put optical. You can see the optical. So for example, the background stars and the foreground stars can be seen in blue. The star that has exploded, that is gone. It's only the remnant. There is another beauty, a star cluster where there is a pulsar called Vela pulsar, VELA, as written here. So it's a very bright in radio. So what I have done, I have put X-ray, I have put optical, and I have put radio. This pulsar spins 11 times per second. So within 1 second, it has rotated 11 times. So the bright light, bright radio emission comes towards us, beep, 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 11 times within 1 second. Period basically 89 milliseconds. So this photograph by GMRT or the image by GMRT has been taken for 5-minute long exposure. So within 5 minutes into 3600 seconds, 5 minutes into 60 into 11. That many beeps has been recorded to create this red pixel picture basically. The contour picture is the red picture. The bright looking pulsar can be seen in radio. Shock cells in supernova remnant, bright looking pulsars can be seen. Similarly, I will show you another thing. This is a galaxy, spiral galaxy. Here, the ultraviolet picture is in blue, infrared picture is in red, and the optical picture is in green. So UV is showing blue looking part. The whole O and B type, 20,000 degree, 10,000 degree hot massive stars, they will explode in 1 million years or few million years. Green, sun-like stars, they have been living for 4.5 billion years, they will not die. They are relatively less temperature, 6,000 degree, for example. The red is a dust and pH. They are not even star. They are like planet and comets. They are 100 degree, 200 degree Kelvin, sub-zero temperature objects. So hot, intermediate temperature, and cold. Very young, old, and something non-stellar. All different components are shown in a multi-wavelength image. Okay. Similarly, a group of galaxies. Each blob is a galaxy here. You can see in this group of galaxies, different galaxies are seen in different color. That means they are bright in different wavelength. This guy is bright in ultraviolet. This is bright in infrared. This is bright in optical. This ultraviolet bright galaxy is having lot of young stars currently forming. Red looking galaxy is having lot of hidden star formation. That is showing lot of infrared emission. This green looking galaxy is a lot of star like our own star. There is not currently forming star. There is not much dust there. So multi-wavelength images are not only just colorful, they are meaningful. You can understand their meaning from the structure and color. Here, the nearest radio galaxy called Centaurus A. I am coming towards close of my talk. Background picture is IOU, infrared, UV, optical. And the contour, the white lines that you see, is a radio emission contour from our own GMRT. So in the blue looking part is the young star, red looking part is the dust and pH, and green looking part is the billion degree star. Sorry, what did I say? Sun-like star several billions of years old. And the radio contours that you see is non-thermal plasma, relativistic magnetized plasma. Means electrons and protons or positrons are moving at 10% speed of light, 0.3 lakh kilometer per second, and they are radiating in synchrotron radiation, radio wave that our GMRT can see. That is what is happening when the matter falls close to the black hole. It shoots out as a bipolar jet-like structure. Like this, a galaxy will be seen green, and the radio plasma that comes out of the galaxy will be seen like two balloons attached to a stick. That kind of things are mostly seen in images with the GMRT continuum. It sees pulsar, it sees radio continuum emission from plasma coming out of the black hole accretion system. It sees H121 cylinder line that I did not discuss much, but that is what it sees the neutral molecular hydrogen. Mostly three kind of tracers are there in the radio. There are many other, but primarily these three kind of imaging: a transient mode pulsar-like imaging, a radio continuum like galaxies and thermal plasma that can be seen in star-forming region, and the H121 centimeter line from nearby galaxies, galaxies rotating around, the gas rotating around galaxies, and far away thing. Okay, so radio galaxies are primarily our focus area of Red at Home. If you join Red at Home, you will be studying how this kind of plasma lobe forms around galaxies and different kind of structure forms. When two black holes merge, what will happen to the jet? Why the jet comes out? What the jet does to the galaxy? What the jet does to the circumstellar medium, circumgalactic medium of the galaxy, etc. You will make this kind of RGB images, red, green, blue contour images, and you will try to find some meaning out of it. And if you do this kind of standard galaxy analysis, that becomes your educational project. But then when you start finding something new, that makes a research project. So when we provide you to look for non-standard sources in the new feeds file, it can be part of the amateur astronomers research project. Wherever you are a student, you can have a project component to your study. It may be part of your course, it may be just personal interest that boost your CV when you apply somewhere else. Okay, I did not discuss much of Red at Home, thinking that some amount of knowledge should be going to you. Okay, not just you know what is Red at Home already. You can look for in Google, simply type Red at Home India. You can find many results. Okay, I think we'll stop at this level and ask for any questions you may have.
Thanks, Dr. Anand. So, anybody has any questions, they can raise hand one by one. We can take up the questions.
You go ahead if you may have any question. Bharatji, say something.
Yeah, Dr. Anand, I have received one question on text
Okay.
from one of our participants. There are people who are joined in a group, so they have just put up one question. These are actually level.
Yes, I cannot see because I lost connection. So
Yeah.
please read that question.
Yeah. So, how do the black holes and galaxy evolve together, and what role does radio astronomy play in studying these processes?
Okay. This is precisely the focus of Radatom Collaboratory. You know, there is something called M sigma relation. What does it mean? Is a smaller galaxy will have a smaller black hole, a bigger galaxy will have a bigger black hole. So, if, for example, our Milky Way galaxy, the spiral galaxy, it has a small bulge. It has a few million times mass of our sun. The black hole at the center of our Milky Way galaxy is few million times mass of our own sun. But a bigger galaxy, for example, like M87, whose black hole image is famous, the Medu Bada-like structure, then that giant elliptical galaxy, the whole of this galaxy is like a bulge. So it has a billion times the mass of our sun. The black hole at the center of elliptical galaxy is billion times mass power of our sun. So what is the problem? Problem is that the galaxy is growing by star formation. Black hole is growing by accreting gas. How does the galaxy know that how does the black hole know when the galaxy how much stars have formed, or the reverse? How does the galaxy know that how much mass the black hole has grown? Why are they growing hand in hand? Why not independent? So that is what is called black hole galaxy coevolution. That in the process of merger of galaxies from the Big Bang, soon after Big Bang till today, galaxies are growing, black holes are growing, but they are growing in well-regulated system. What is the regulation process? Once the black hole is growing, how does the black hole communicate to the galaxy that stop growing, overgrowing? You have grown enough. I have grown this much. So that is what people believe, that when the black hole grow, means when they accrete gas. When they accrete gas, lot of radiation and radioplasma comes out. So in the process, when the plasma and radiation comes out, the cold gas of the galaxy is blown away. When the cold gas is blown away, there is no future star formation. This is what is called AGN feedback model. So a lot of people believe in this, but what we are looking for in red atom is the smoking gun evidence that this process is actually has happened. Okay, black holes and galaxies grow hand in hand. How it is correlated through the radiation and jet outflow from the center is not clearly known, but it is definitely believed by most of the astronomers.
Okay, thank you, Anand. We have Anup Karekar who has raised hand. Anup, over to you.
Excellent talk, sir.
Thank you.
Sir, my question is, how can we be part of your research project? So, like, do I have to join your Facebook community or to do a specific email or something?
No, if you
I
are
mean,
a
that is a question most of the people are asking to us.
okay,
Also. Like,
okay,
how can, as a student,
okay.
join the RAD at home for the astronomy research?
It's very simple. If you are a student in a university or college, or you have completed your BSc, MSc from any university or BTech, any university anywhere in India, so you can simply join the Facebook group. I come there for discussions and training and discussions every Saturday 2 to 4. And anytime you wish, you can make a galaxy image, post your galaxy, and discuss there. So if you are a student or you are an alumni of any university, you can join as a member there. But if you are asking like a astronomer, or for example, you are a lecturer with a PhD degree in science, you write an email to me. We will discuss different way of joining the collaboration. There are different terms and conditions for PhD degree holders to join the Atom collaboration.
Okay.
Okay, join Facebook group. That is simple answer.
Okay. We
Okay,
have
sir. Thank you.
more questions in chat, Anand. How GMRT will remain relevant with the SKA completion?
Okay, this uh, the question is very simple, but it's not so straightforward to answer. The point is, after 8-meter or 10-meter class telescope in the world, does the 2-meter class telescope become irrelevant? No. For example, SDSS is a 2-meter class telescope. HST is a kind of that kind of a telescope. So all the telescope, irrespective of their size, they have many other ways of making impactful research. Before SDSS, there was no digitized sky survey of the sky. So SDSS being small, most of its time has gone to surveying the sky, and many papers have been written. So there are parameter space is different. For example, you can go deep with a big telescope. People want to go deep and see what is happening close to the Big Bang, for example. If you have a small telescope, go wide. What is happening to all kind of galaxies? Survey. If you have SCA in the future, it will be extremely competitive to get a time in SCA. So people will go for very selected PI driven kind of study. So at the same time, SCA will also have a survey system. So whatever was found from survey, one can go for a deeper observation with the GMRT. So the small telescope and big telescope are having their own competitive edges. And GMRT being still being completely a world-class telescope, it is being continuously upgraded. Today it is UGMRT. There is no frequency range that it cannot observe in this band. There is no telescope in the world which is as sensitive as GMRT in this frequency range, in this 150 to 1400 megahertz range. Below LOFAR can be sensitive, above VLA can be sensitive. So there are galaxies which can be seen for their H1 emission in this range only. So the SCA will be there. There will be some parameter space that this polar telescope can address, survey or depth or follow-up, whatever it may be. Okay.
Okay. We have one more question. Aryan, you want to take up? Aryan Arvind, you want to take up the question?
Unmute yourself and ask. If you cannot do, we'll read his question.
Yeah, he's come. He's asked.
Okay, he has a problem probably. How does a galaxy form? Okay, so in the beginning, when the universe cooled down, okay, his mic is not working. When the universe cooled down from a phase where the energy of the particles and energy in the photons are completely comparable, that time universe was opaque kind of thing. When it started cooling down, hydrogen atoms started forming. The proton can be started attracting the electron. If the electron has very high energy, it will not be bound. So that was the high energy phase. When it became bound, it became hydrogen atom. When a group of hydrogen atoms, you can call it a hydrogen cloud, when the cloud started cooling, it started collapsing, contracting under gravity, because there is too much of energy, thermal energy. Gravity cannot pull it towards the center. If it is having some low energy, gravity can start pulling it towards the center. So a cloud formed. Once the cloud forms, then actually stars will start forming. When the stars form, nearby cloud, nearby star, they start going around their center of gravity. That is how dwarf galaxies, small cloudlet forming stars formed first. Then small spiral galaxies started forming. The spiral galaxies started merging. They started forming elliptical galaxies. This is how in the universe today most of the galaxies are either spiral or elliptical. There is very many similarity with the way cloud forms and hailstorm form there. Water drop forms there in our atmospheric cloud, water cloud.
Okay, thanks. We have one more question from a school student. What should I study in school if I want to become an astronomer in future?
Okay. You do not have to study anything special in the school. Do your proper coursework properly. Your focus should be mathematics and physics. Without mathematics and physics, you cannot grow in astronomy also. And do not shy away from programming. Learn programming, computer science always, because computers are omnipresent. Coding, computer science basically, mathematics is the language of physics, and physics. Continue studying these things until in your BSc, BTech or MSc, PhD system, you have an option of selecting astronomy over nuclear physics, condensed matter physics, that kind of thing. Otherwise, basic physics is common everywhere. Better physicist you are, better astronomer you will become. Chetan has put a question.
Yeah.
For optical region, Chetan, do you want to ask?
Yes, actually, you discussed like from optical region, we can seeing colors, we can figure out what kind of star formation is taking place. So for radio region, what kind of different processes we can figure out what things are happening? Because I think can you just elaborate somewhat on those?
Okay. Apart from synchronous radiation, the radio radiation that star forming region give is something called free radiation. Okay, free radiation or thermal Bremsstrahl law. So if a star forming region is looked at in optical, infrared, and radio, the radio can give you a dust free picture of the ionized gas in that star forming region. Optical people cannot see what is hidden in the dust cloud. Star may be forming there, star may be there, but they cannot see. Infrared, on the other hand, it will show up the light that is passing through and re-radiated by the dust. But the ionized gas, which is ionized by the ionizing radiation from O and B type stars in those star forming region, can be seen by radio. So dust doesn't affect radio. To have a complete picture, upper surface ionized cloud in optical, inside dust and pH in infrared, and ionized gas deeper inside can be seen by radio. There are radio recombination lines also. So the ionized gas clouds, which are, say, in Niels Bohr model, we have studied n equal to 1, 2, 3, 4, that kind of transitions. But n equal to 100, n equal to 200, that kind of lines, that kind of jumping lines can be seen in radio also. So that kind of high Rydberg number lines can be seen in radio in spectral line. So kinematics, amount of estimate of ionized gas, that kind of things can be studied in radio. If it is continuum, it's a imaging. If it is spectral line, it can be recombination line also. Recombination line is a bit difficult, but it is possible with radio telescopes, big radio telescopes.
Okay, thank you.
Thank you. We have one last question from one of the participants again. What are some of the most exciting discoveries made using GMRT? and how they have impacted our understanding of the universe.
Okay, it's a journalist-like question, but every common man will ask this thing. See, GMRT, if it has contributed significantly to few things, there is definitely the merging of clusters of galaxies. When the two clusters of galaxies merge, they create a lot of shock waves. And the shock waves are very feebly seen in any other band with any other telescope. But they will be prominent in the low frequency. So when GMRT started functioning around 2000, for 10 years, GMRT dominated this shock cell and the outflow from the central black holes in clusters of galaxies, called a black holes feedback. The cluster field of cavity and shocks was the major contribution of GMRT. Okay, this is continuum imaging. I will come to one more point. The H1 or atomic hydrogen that gives 21 centimeter line is seen in GMRT band is very difficult to detect far away. The signal strength becomes very little because GMRT has 3 times bigger collecting area than the American telescope VLA. It is the best telescope to detect H1 line from far away atomic hydrogen clouds. So the current record of highest redshift H1 line detections is actually held by GMRT and nobody can beat it till now. Okay. Coming to the third point, there are, I don't know it is true or not, but it may be a beating of my own drum, but there are special kind of radio galaxies that has been found. Radio galaxies are millions of them are known today, but special kind of radio galaxies were found which are hosted not by elliptical but spiral. And Indian astronomer using GMRT had led this field, including me. Okay, that is how I was saying it's maybe a beating of my own drum, but it is true that the kind of analysis that GMRT could provide, because of its instrument has its special nature, we are best in the system. It's seen in this kind of imaging spectroscopy and transient mode. What is the last thing I will tell is that the gravitational wave connection. People looking at faraway pulsars, they can see what is the magnetic field changing in between, how the pulse from the different stars, different pulsars change. As the gravitational wave passes through, it compresses the space and extracts kind of thing. It's an oscillation in the space itself. So the distance traveled by those pulses reaching GMRT are varying in time. So the very low frequency gravitational wave detection is possible with radio telescopes. And GMRT being very good in pulsar study has contributed to this analysis, this discovery, low frequency gravitational wave detection. So I would say these are the very major significant growth contributed by GMRT to the astronomy field.
Okay, thank you. Anybody has any other questions? Anyone has to ask any questions in chat or in person? I think no. I think it's already 6:26. So thank you, Dr. Anand. We extend our heartfelt gratitude for your insightful session in AstroTalk 33 on exploring the universe with radio astronomy. Your pioneering work with the Rad at Home and contribution to citizen science research have inspired us all. Thank you once again for sharing your expertise on GMRT, black holes, and cosmic discoveries, making astronomy more accessible to enthusiasts and people who love astronomy, astrophysics, radio astronomy. Definitely, your passion for the science education is truly commendable, and we look forward to more enlightening discussions or sessions in near future. with respect to that, we thank you with Amateur Astronomers Association Bombay and Bharat sir. Bharat sir, you want to add anything?
Only I will say, uh, I'm sorry my voice is breaking up, but it's a vote of thanks to Anand, primarily for giving a talk uh, in a span of just 4 days. He had a talk earlier also. Thank you, Anand. And it was nice listening to you. And uh, we will look forward to listening to you more. Thank you very much.
Thank you. Thank you very much. Thank you
Thank
very
you,
much.
Ajay. Thank you. Thanks all everyone for joining the session. With this, we will conclude today's session. Thank you very much.
Thank you
Thanks,
very much, sir.
everybody. Bye.
Thank you very much, sir.
Thank you. Welcome. Bye.